Dear ladies and gentlemen, my name is Mirosław Ferdynous. I am from Poland and I work at Lublin University of Technology in the Machine Design and Mechatronic Department. I am co-author of presentation entitled Identification of Crashworthiness Indicators using artificial neural network on the example of columnar energy absorber with triggers in the form of cylindrical dents on the lateral edges. How to the presentation I am now giving is a continuation of the work I presented a year ago. A few words by way of introduction. One of the key aspects of passive safety is a properly designed crumple zone, of which crashes boxes are very important element. Crash boxes are mounted on the side members inside the engine compartment, as you can see in the picture, connected by a rigid beam which is hidden under the bumper and is designed to absorb energy in low speed crashes up to 1590 kilometers per hour, protecting the side members from damage, which is costly and time consuming to repair. If you look closely at the crash box, you can see the embossing, which is very important in the crashing process. The geometrical parameters of that embossing are crucial for the energy absorbing performance. A few words to help you understand the meaning of the indicators that will be considered later. A typical crashing force versus shortening characteristic is shown on the right. The area under the curve is measure of the energy absorbed. Very important are the terms of peak crushing force PCF and mean crushing force MCF, clearly visible just in the graph. Designers of crumple zones must meet two main, often conflicting requirements: minimizing the initial peak crushing force while maximizing the amount of energy absorbed. This is where modern techniques using neural networks can have a great adventure in finding optimal solutions and predicting the geometrical parameters of the trigger in order to achieve the desired effect. Okay, sorry. Let's move on to discuss the object. Sorry. Let's briefly introduce the terms we use in the field of crashworthiness. I have already mentioned first one, energy absorbed, as a field under the curve. Another term is mean crushing force given by the formula visible on the slide. Let's move to the first important indicator, which is the focus of the energy absorber's biomechanical properties, called crash load efficiency, as the percentage ratio of mean crushing force to initial peak crushing force. Another important indicator is stroke efficiency, SE, which is the ratio of the crash distance to the initial height of the energy absorber. Some researchers express these two indicators in one called total efficiency, TE, which is a product of crash load efficiency and stroke efficiency. Let's move on to discuss the object of the research. The subject of the study were thin-walled aluminum tubes of square section, as you can see on the slide, with 4 dents formed by cylindrical embossing at the corners on each tube, as you can see at the figure. I have you already noted that importance of the triggers and their geometric parameters. The research program included numerical calculation of series of models in geometrical parameters of embossments, one of which was validated by experimental. A total of 121 models were analyzed in order to obtain values for the crashworthiness indicators. The range of diameters of embossing D was from 20 to 80, and its depth G from 2 to 8. The position H of the triggers was varied from 20 to 100. On the figure, you can see a construction drawing of the column. Model designation system has been adopted. The first letter denotes D means dent. The subsequent dash gives the diameter of the trigger D, its depth G, and its position H. An analysis of crashing behavior of tested columns was carried out using FEM simulations. The Abacus code of explicit method was used, and here I will spare you details, some of which are visible on the screen. If you are interested in person, I would happy to discuss it behind the scenes. Let's move on to the discuss verification by experiment. Due to time constraints, I will treat it laconically. Impact tests were carried out using instrument test drop hammer ring, a general view of which is shown on the left, but also a specimen mounted on the measuring table with the piezoelectric force sensor is shown next to. Specimen designated as D46H30 was selected for verification testing. On the right, you can see the crushing force shortening characteristic. You can observe that the curves from the 3 experimental tests are really close also in terms of maximum shortening. Above the graph, you can see deformed specimens after the test and the shape of the deformation obtained from FEM simulation. The table at the bottom shows the results of the indicator calculations and the differences between the experiment and numerical simulation. In the last row of the table, you can see that the differences are really small, which shows the quality of the numerical model. The numerical simulation carried out leads to a crash force versus shortening characteristic, which in turn allows the PCF to determine and the other crashworthiness indicator rates to be calculated. You can see one group of characteristics. It can be seen in the initial phase, marking by ellipse, the action of the triggers with different geometrical parameters. Here, the exact results of indicators calculation of 121 models. Please note the depth of embossing affects the PCF and therefore crash load efficiency. As the depth of the trigger increases, the PCF decreases and the crash load efficiency increases. And you can see here that the key factor of the depth is the depth of the trigger, not the diameter. Here are the next results. As you can see, certain trends are visible, but with so many factors, the position of the trigger introduces certain imbalances. Only the use of modern tools allows trends and relationships to be captured. And the next results, and the presented result of the calculations became the basis for building a neural network. Two types of network were tested, but more on that later. Multi-layer perceptron network study. Neural network are signal processing mathematical models. The most popular structure of artificial neural network is multi-layer perceptron. The network model consists of numerous neurons set in layers. Regardless of the types, each neural network uses numerical input values and set numerical output values. I'm not specialist. Triggers, geometrical parameters, and its position were taken as input variables. The values of peak crushing force, crash load efficiency, stroke efficiency, total efficiency indicators from the numerical experiment are the output values. Figure shows one of the most frequently used activation function used in the research, S function. Two multi-layer perceptron neural networks were used in the numerical study with 5 and 4 neurons in the hidden layer. Table 3 leads the values of the training rates for the multi-layer perceptron networks with respect to predicted indicators. As you can see, the network is achieving quite good quality. The sensitivity analysis showed that the depth of the trigger in most important parameters, and as you can see in the table 4, another important parameter is a position of the trigger, age, and least important is the diameter of the dent. Table 5 shows that the parameters of neural network, expect stroke efficiency, show the high correlation for all data sets, training, testing, and validation. The distribution of residuals, namely the differences between the output variable and its predictor, was examined and shown in the figures 3, 4, and 5. For both active networks, the histograms indicate that the residuals are more or less normally distributed around 0, which is in line with the general assumption of normal noise in the data. Figures in the bottom row show the relationships of the results obtained by the neural network depending on the actual values. These graphs show the effectiveness of the two multi-layer perceptron networks analyzed. In the following slides, I will present the values of analyzed indicators depending on the geometrical parameters and trigger position obtained as a result of the network. Here are the peak crushing force values depending on the depth and diameter and the depth and position of the trigger. Here are the crash load efficiency values depending on the same input parameters. It can be seen that the highest crash load efficiency indicators obtained for maximum embossing depth and minimum embossing diameter. And here are the stroke efficiency values depending on the same input parameters. Finally, total efficiency depending on the depth and diameter and the depth and position of the trigger. Final conclusions. The conducted research has shown that artificial neural network can be applied to predict the values of crashworthiness indicators with acceptable error. There are minor differences between the network models with 4 and 5 neurons, networks in the hidden layer. Quality differences between are below 2%. From the network sensitivity analysis, it can be concluded that by far the most important parameter of the performance of the models is the trigger depth. The overall quality of network performance was about 90% for the training set and over 97% for the test data. in order to confirm the universality of the neural network performance, and additional numerical experiment was introduced. The random models, including two with parameters outside of the range that was used to training the artificial neural network, were tested. Uh, Out of range model was signed by the rectangular. Uh, the five neurons network had marginally better performance, so its results uh, will be presented due to lacks of time. Regarding to the prediction of PCF values, the maximum differences are 2%. Regarding to mean crashing force as and crash load efficiency, maximum differences are obtained for out of range models and amount of 6%. In the prediction of stroke efficiency values, differences were also obtained for the out of range models and amounted to approximately 5%. Good prediction properties are shown when it comes to calculation of total efficiency, which is after all the product of stroke efficiency and crash load efficiency. As a practical aspect of our research carried out, it should be emphasized that the use of multi-layer perceptron can successfully speed up the design process. Thank you for your attention.